Okay, good morning, guys. Problems, questions, observational remarks? What was we talking last time about?
The ramp compensation.
Ramp compensation for the error between peak value and average value in current model CCM system. So, time IL, this is the actual IL. We are at CCM, and most of the time if we are in this condition it means that we are designing a buckle or bumpy right word. And this is the limit, I peak, I1, and obviously there is an error. So, we learned that in order to know this error, bring it to zero, you need to add the peak value that we want, a sort of a compensation ramp, something like this. And obviously this red curve must be shifted down a little bit in order to get the point of the peak value is just the average value we want. And we learned that this slope must be
minus V over 1 out. V over
negative V over S. Obviously we don't compare the actual inductor current with our inductor current. We compare voltages. So this curve will be multiplied by RS, by extending coefficient equation. But that was the basic idea. Well, this ramp set brings to zero the audio susceptibility, makes my system work without any approximation, because you remember I approximated earlier that the peak value is almost equal to the average value. It's not true. This way it's okay, but it's not the best reason to introduce a compensation ramp. The reason for compensation ramp is the very bad problem of current mode converters, current mode control, that is the subharmonic instability. Let's suppose that this is our I peak, and this is my IL. If a cycle starts with the wrong value of current, here for example, this is the initial value. Why? Because the previous cycle made some mistake. There was a noise that closed too early opened too early the switch. So the next cycle will start with a current that is lower than that should be, and we have something like this. The peak control keeps the peak at the same value. But doing this, I end up with the final current that is too large with respect to what I want. So the next cycle will start with a current that is larger than this. It will reach immediately the peak value and will come down over here. Ouch! We already determined that this amplitude becomes larger at the end of this cycle, becomes even larger at the end of this cycle, and we are in a condition of diverging error. Why? Because the duty cycle is larger than 50%. Well, a way to correct this error is to introduce a compensation ramp. But the compensation ramp to cancel the subharmonic instability is different from the compensation ramp we saw last time. What's the idea? The idea is that at the end of this cycle, I want my current to be over here. That is the right value. So, if there are no errors, it ends up exactly like here. If my initial current is too small, well, what should I do in order to end up at this point? Well, I should open my switch in any time along this straight line. That means if my current initially starts too low, it ramps up with the same slope, And when it arrives over here, I have to open it. So when I open it, it ends up at the right level. What if my current started too high? If my current started too high over here, ramps up, and at this point I have to open the switch, because if I open the switch over here, current will come down, still with the same slope, the slope for a buckle is negative V naught L, and will end up at the same point. So if I add a compensation length with this slope, I will kill any subharmonic instability exactly one cycle.
In this case, I'm not changing the IR level. No.
In this case, I'm changing the IR level. Yes, I have to move it a little bit up or down. I have to introduce an offset. But I am not worried about this because the offset is controlled by the integrator that is in front. If I add just this compensation lamp, I change the level, the average level, for sure, because this lamp is not the ramp I introduced over there to compensate for the difference between peak and average. Here, the difference between peak and average is still there. But what happens is that there is no more subharmonic instability. What about this error? This error is compensated by the integrator that just changes the peak value in order to get exactly what I want. So compensation ramp is needed, is a must. Every time your buck-to-derived converter works with a duty cycle that is larger than 50%. And this is the case. Quite often when you design a high-power buck-derived converter, your duty cycle is for sure larger than 50%. So this is something that you really need. What's the slope or the compensation ramp you need to end each cycle exactly at the right value to kill your subharmonic instability exactly in one cycle? That means what is this slope?
Minus V over.
Negative V over Z over F. That's it. It's twice as much as the ramp that cancels the average error with respect to the peak average. So if you want to kill the subharmonic instability in very few cycles, in one cycle, theoretically, just use this compensation slope. And observe that it's nice in buck converters that output voltage is constant most of the time. So this compensation ramp has a fixed slope, and you can add it as we did the last time, not on the controller voltage, but on the other side of the comparator. So we add it on the voltage we read from sensing, current sensing. Okay? Compensation ramp needed for current mode if your duty cycle is larger than 50%. And then, before going to the practical details, and practical details are painful in real life for current mode. Before going there, I would like just to discuss a little bit the number of poles in a current mode controller, CCM. DCM is a different story. How many poles do we have? Well, we found out last time that a buck converter, a buck-derived converter, looks like more or less, with a good approximation, as a controlled current source with our output capacitor and load resistance, like this. And so we have one pole. One pole at 1 over 2 pi C, the load resistance and the output capacitance. And this is what you need for practical design, most of the times. But you remember that we started from a circuit like this, and this result was the very first that was found out and was okay. I think it was by Middlebrook then. Then somebody else started to notice around, to look at this circuit and say, oh wait, but there are two elements with memory, two elements storing energy, so they are described by differential equation. And if you consider that you have a feedback over here, current feedback, and you go to a controller and you go to control the switch to keep the inductor current constant, that is just a feedback. Feedback cannot cancel, cannot destroy, cannot manipulate a pole. Feedback, give me the magic word, moves poles, scatters them around, but does not cancel them, does not remove them. They are still there. They are just moved away. So, somebody started to look for the pole associated to the inductance in this feedback loop, and he discovered that this pole is moved to high frequency, above 1/2 of switching frequency or somewhere like that. And so, if we have to discuss the number of poles, we can say, technically speaking, we have one pole. This is what you do when you make a design, most of the time. But somebody else came out and said 2 poles. One is at 1/2 pi C output capacitor times resistance. The second one is at high frequency, above, it's around the switching frequency over 2 and above. So it's not giving you too many troubles. Because if you have a high frequency pole, this pole can decrease your phase margin, but not too much, because your crossover frequency is around switching frequency over 5, over 4, over 6, over 10, something like this. And so if this pole is quite higher than the crossover frequency, the phase reduction you get from that pole, from this high frequency pole, is not so important. Okay? People was happy with knowing that there are 2 poles, one is high frequency, who cares about it? And then somebody else came out and said, no, wait, there are 3 poles. And the guy who came out with the 3-pole idea is Ilpk. Because he said, if you have a subharmonic instability, if you have an unstable system, it means that you have poles that are very close to the imaginary axis, or they are on the right-hand plane of the S-plane. And what's the frequency of the subharmonic instability? 1/2 of the switching frequency. So, Ilpk came out with this idea. We have one low frequency pole, the standard 1/2 pi RC, and then in order to describe this oscillation, we need 2 complex conjugate poles at 1/2 of the switching frequency. And these 2, this is a slow pole, a low frequency pole, so it's close to the origin, and the 2 complex conjugate poles are high frequency poles because they are 1/2 of the switching frequency. And according to the duty cycle, these poles can move to the right-hand plane. When the duty cycle equals 0.5, these 2 poles that are there move to the right-hand plane and the system becomes unstable. And Ilpk was able to prove this idea, came up with a lot of calculations, but the basic question is, what? In order to have 3 poles, we need 3 elements with memory. Where are they? Flip-flop. Flip-flop that is here, the feedback control, current control feedback loop, is a memory element. It's non-linear, but it's a memory element. So in some cases you can justify this is just a hand-waving proof, it's not a rigorous proof, that you have 3 poles and this model is correct. So this model tells you that you have one low frequency pole, that is what you have to worry about, and these 2 poles that can move to the right-hand plane if your duty cycle increases above 0.5. If you add a compensational lamp, these 2 poles are moved to the left and you don't have to worry about it. Okay? That was the situation in the 90s or a little bit later. And then somebody else came out and said, no, everything is wrong. You have an infinite number of poles that are quite hard to compensate for because you never end to compensate for them. Actually, this infinite number of poles is just a time discrete representation of our system. Instead of using Laplace transform, we use Z transform. In Z transform, you can describe your system very well, but when you go back from Z transform to the Laplace transform, you have an infinity of poles around the vertical axis or something like this. Don't worry about this. This is a good idea because this tells you that you have instability, and these two poles have a Q that depends on duty cycle and the compensation length. So you can add a compensation length that keeps them to the left, far away from the imaginary axis. This is basically useless because we don't need it, and this is what we use. Even if we use the three-pole model, this is the important one. And then you have to keep this on the left-hand side. Okay? So far so good. In some cases, if you use this model, the two-pole model, the high-frequency pole could move down as low as a switching frequency of a line. But don't worry too much. It's just a model. It's not reality. Reality is a couple of poles. This is quite real. This is just a model. This is just a pole that describes what happens, but it's not there actually. This is a little bit more physical, maybe because this can allow you to foresee that there is a subharmonic instability, but you don't see the phenomena of period doubling that I told you about last time. And this is just a mathematical stuff. Did you look for Mr. Feigenbaum?
Qualcosina ho visto.
What is related to?
Non ho trovato
Feigenbaum will work on the boost converter, on the buck converter, on the current buck converter. No, he didn't. Feigenbaum is a mathematician, and
there's a constant of Feigenbaum. There's some value that give a relation about the how near the solution, the increasing of solution are when we move on an x-axis.
Yes, something like this. Feigenbaum constant gives you the ratio of bifurcation points, and tells you how quickly you get that point where everything becomes very complicated. That has a technical term that is chaos. This is the buck converters can go into chaos. The current buck converter, because if you have here the ideal D, here the actual D, up to 50% everything is fine, more or less, and then it starts to bifurcate, so you have a cycle between two values, then it bifurcates again, and then it goes on more and more, and each bifurcation is closer and closer to the previous one, and the ratio of how much those are closer and closer to the Feigenbaum constant. You have an accumulation point of bifurcation over here. At a given point here you have chaos. If you keep going on, a very characteristic, a very important signature of chaos starts out, and you have 3 duty cycles. Period. It's not multiplied by 2, by 4, by 8, by 16, by 32. When you get infinity, you get chaos. After a while, you get 3 different duty cycles that are repeated, and they start to bifurcate again. And you have another stuff. This is mathematical. You don't need to go over here. When you are here, you are already in trouble from an engineering point of view. I think that yesterday I was working on a Buggy-like converter current model. It was exactly here, chaos. But that was not a mathematical chaos. It was just due to noise, electromagnetic noise in the circuit. Okay? So far so good. So, we have still fewer subjects about the current mode, and these subjects are current mode on buck-boost converter, DCM. Does it work? Is it useful, etc.? And we have the practical aspects of measuring the current, where to measure it and how to measure it. And where to measure it, we can show it and see it this way. Let's take buck converter, the in, read not, and if it's not a buck converter, the important part is that you need to understand the idea that is behind it. And you can say, okay, I need to measure the peak current, and when the peak current is reached, I open the switch. That is the basic definition, the basic rules for current mode control. When may I go to measure this current? Well, I will just pick randomly a lot of sections over here. I could say, okay, I could measure it over here, could make point 1, here, section 2, section 3, section 4, section 5, and just count over here. Oh, here, section 6, section 7. Every time there is a wire, I cut it and say, I try to measure my current over there. For a buck converter, this is easy, but you have to be able to see these basic ideas on any kind of converter. Over here, 8, here already done, over here, 9, over here, 10, over here, 11. Well, 11 and 6 are the same story, but there is a different story. Here, 12, could be here, but I don't want to go too much into the text. There are a few of these sections, of these measuring points that are okay, a few that are basically totally wrong. And let's start to discuss for each of them if it is okay or if it is wrong. Remember, I want to measure, what do I want to measure? The peak current of inductor. Because that is when the inductor current reaches the peak, I want to open. The peak that I set for this working condition, I want to open the switch. Is this okay? Do I see the peak current if I measure the current over here?
Yes.
No, why not? Because over here there is just a DC current going in. All the ripple that is carrying the information on peak value is just passing to the input capacitor. So this is a no. This one. Do I see if I measure the current over here, do I see, for example, you can imagine I put my current probe here around. Do I see the peak value of the inductor current? Yes. Yeah, sure. This is okay. What about this one?
Same.
It's the same. What about this one?
I see.
Sure. It's exactly what I want to measure. So, no doubt that these two are okay. What about this section number 6?
I see.
Is there the inductor peak current flowing through here?
Yes, I see during the first moment of T off.
First, what?
The first instant of T off. I see.
I say when T off starts, I see this current. So is it okay or not? It's like that guy who climbed a tree to trim it for time to trim a tree, and was sitting on a branch and was cutting the branch between himself and the stem. Here you have the peak current at the beginning of T off. But in order to start T off, you have to measure the peak current. So if you go over here, there is the peak current, but not at the right moment, because you need the peak current during T on to measure during T on. And this is during T on, here current is 0. So this is no. What about 8? That's a no. Why? You see, it's just the average value. What about the current flowing to the output capacitor? Oh, I forgot the input capacitor.
No, because there is also a secret.
The current flowing through the capacitor is AC only. There is not the DC value. So when I use a current not controlled, what I need is the total current, not just the current rainfall through the inductor. I need the actual current. How many amps are really passing going to the inductor? So this is a no, unless you have a different way to establish what is the DC current through the inductor. In this case, you could use this one. There are techniques of control like IVI, integral voltage on the inductor, that can use this ripple current, but not a good idea. And this is also not a good idea. 9. Do we have the peak current flowing through the section number 9?
Yes, yeah, because it's the inductor current.
Yes, inductor current. Is it a good position to measure the inductance, the current of inductor? Well, that's just a yellow. It could be, but remember that you have doubts, because if you connect it to the ground, this, no, because it's the negative of the relay, and you connect to the ground, this node, you are just basically shorting this current section. So the current that flows back flows partially through here and partially through the ground, the connection, and so you would measure all the current. And the same story is over here, but here is even worse, because even if you are smart enough not to connect to the ground at the output negative side, what happens is that the voltage that is across here, because when you sense a current, you generate a voltage for sure, the voltage that drops across here is a pulsating voltage, so you have your output voltage, the common mode output voltage. Remember, we already discussed this when I tried to move the switch on the lower side. This will have a common mode voltage that goes up and down and could generate noise. Not too much, it's not as bad as placing just the switch on this side, but it's a bad situation. And what about, I didn't put any number, but what about this capacitor? That is no, because we have only the AC value, not the DC. So it seems that the good sections are 2, 3, 4, 5. What about 11? 11 has an advantage, unfortunately it's measuring the wrong current. Okay. 2, 3, 4, 5 are the good positions, 9 and whatever is this one, 10. Theoretically they work basically in practice. In real life, not so much used. Now, we have to go through 2, 3, 4, 5 and see which one is better, which one is worse. And we can group these sections like 3 and 4, we put them together. I mean, they are in the same class of good or bad, and 2 and 3 are in the same class of good and bad. No. 2 and 5. And on the other hand, 4 and 5 are in one class, they share a property, and 2 and 3 they share another property. So let's start to see how is the voltage over here at this node. How is it? I understand that the question is very vague and it's a DC voltage. It's big. DC voltage here you have big DC voltage. What about the voltage over here? Just observe that current over here is absolutely the same. The current in 2 and 3 is something like this. What about the voltage in 3? Section 3.
Square wave.
It's a square wave. What about the voltage in 4?
Square wave.
Is it a square wave? What about the voltage in 5?
More like DC.
This is a DC. Yes. So 3 and 4 have B noise That means they are swinging up and down from 0 to Ving to 0 to Ving. And in some cases you could have a problem to measure it. We will see it in a moment. On the other hand, 2 and 5 have DC voltage across them. So they are weak wired. This section and this section are better if you want to measure the current, because here your voltage is constant, here your voltage is constant. Then we will still do argument on it. 4 and 5, what do they have in common? This time not regarding the voltage but current. They have the same current exactly as 2 and 3, but what's the current difference between 4 and 5 and 2 and 3?
Four and 5 have the same current as continuous.
This is the current of 4 and 5, and this is the current in 2 and 3. In both cases, you can see when you reach the peak value. Here you have, let's say, not so noisy current, just a small ripple, no steep edges, but you have a large DC current flow through. Here you have a lower DC average value, but you have a high frequency noise due to the edges. Okay. So in general, we will go to measure, to sense the inductor current either here, 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 or here. 4 of them, all 4 of them I use. Probably only the number 4 is not used. 5 is used, 3 is used, 2 is used. I stay in any case for 5 and 2 because there is less noise, more less noise. But let's see, which one do we pick? Because we have 4 possible candidates, and which one to pick depends on what technique you use to sense a current. So, tracing. There are, as far as I know, 4 or 5 ways to measure a current, but only 2 of them are usually in practical use, in everyday use. Give me a way to measure a current, to sense a current. A meter, yes, but we don't need to have a meter that moves up and down at 100 kilohertz or 200 kilohertz, or a display that changes at 100 kilohertz or 200 kilohertz. We need this current, the current measured on those sections that we discussed earlier, to send this current to the comparator and to see when we reach it. We are the maximum inductor current we have to open the switch. So, shunt resistance. RS, just a shunt resistance. And we get a voltage over here that depends on the current. My friend George Simon told something important about it, something like V equals R times I. So we decide what voltage we need, what current we expect, and we decide and we determine this resistance value. Another way to measure a current.
The probe with the Hall effect.
Hall effect, yes. Hall effect probe. This is used in large power circuits, especially inverters or larger systems. When adding, you have low frequencies, not so high frequencies like in our circuit. And the system is so large, so expensive, that adding a few euros of Hall effect sensor is not a big deal. If you are trying to build AC adapter for a laptop that has to cost $7 to material. Then you sell it at a higher price, but the cost is around $10 or so. You cannot add a component that costs $1 or half a dollar. That's too much. And by the other way, an AC adapter works at high frequency, a few hundred kilohertz, and all effects don't work well at high frequency. They're okay up to a few tens of kilohertz or less, and they are expensive. So for large power systems that are low frequency, relatively low frequency, and are expensive, adding $10 or a sensor is okay, but not in our class. This is the reason why it's in the third position. Tell me, talk to me. You want to measure a current in a wire? What you could do is to use current. Well, if you say current mirror and you think of the two transistors connected together, it's not really like this. But it was done. There was a device that was designed to work as a current mirror. This device was basically a large MOS transistor, and in the same piece of silicon there was a small MOS transistor in parallel, and that means that just a large area was just disconnected in one part. And the two gates were together, the two drains were together, and two sources were separate. And so, that was a big transistor, big area. This one had an area that was equal to 3 divided by 1000. And it was very easy, because with silicon die, you have many cells making forming this transistor, and you just pick one cell and you don't connect the source with the other one. If you put the two sources at the same voltage, this is important, what you get is the current over here is 1000 times the current over here. But then you still have to measure this current. And one way to measure this current, and to keep the source at ground, because if this source is not at the same voltage as this source, current sharing is not working as the ratio of the areas. So we put here a current to voltage converter, a transient resistance amplifier, something like this. It was a very bad solution because this costs more. Why does this transistor cost more? Because it has 4 pins, not only 3. So you need a special package. Then you have to add an op-amp, a fast op-amp, because you wanted to see the instantaneous current flowing through here. And then this fast op-amp had to give you an output voltage that is negative, because if the voltage here goes in, so the current goes down like this, flows through the feedback resistor, going to the right, and the left hand side of the resistor is a 0 volt, because negative input follows the positive input, inverting input follows the non-inverting input. Here you have 0 volts, here you have a negative voltage. So you have a negative voltage less than 0 volts, here the output. Usually your control circuits don't have double symmetrical power supplies, positive and negative power supplies with respect to 0. There is just a single supply. And so you need a positive and negative supply voltage for this op-amp, and the pure circuit can be able to handle negative voltages. So that was a good idea. One more that is used.
With op-amp. Thing that they used.
No. Wait a moment. The current we want to measure is in the order of amps, or many amps, for a factor of an amp.
Cannot we use the inductor itself?
Can we use the inductor itself to sense the current? You are reinventing a technique that is used, but it's not so easy. Because how do you want to measure the current using the inductor?
Using the inductor as a transformer.
Using the inductor that you already have as the primary winding on transformer, you put a secondary winding in the same core, and you get some information about the current flowing through it. Unfortunately, and this is the problem, current flowing, the current transformer, the biotransformer, cannot be DC. If you have a DC current, then it's not transferred to the secondary winding. If you do something like this, that means you add another winding on your inductor, you get a ripple. That's okay, but not the DC value. But transformer is the right solution if you can do something about it. And this is the current transformer. In some cases, you need to use a current transformer, otherwise it's a big mess of power dissipation. So the two main methods are sensing resistor and current transformer. At this point, knowing what we can use to measure, to sample, to sense our current, we can go back to our circuit and decide where we can use a current transformer, where we can use a sense resistor. For example, can we use here and here? That means exactly across the inductor. Can we use a current transformer over here or over here? No way, because here there is a DC current that we cannot get rid of. So, in these two sections, the only solution, the only possible solution is resistance. And if you use a resistance, you put a resistance over here, you have a voltage drop V equals RS times I, and this is the differential voltage across the resistance. But if you get not only, if you want to evaluate not only the differential voltage across the resistance, but also the common mode voltage, the average voltage of these two nodes, you see that the average voltage over here is about the output voltage, constant, DC. So you can use a differential amplifier that cancels out this, does not sense this common mode voltage, this DC voltage, and this is a good place to put your resistance. On the other hand, if you go over here, you get exactly the same voltage drop. But the voltage at these two nodes, the average voltage across this resistance swings up and down from 0 to 8. And so your differential amplifier, because it's a differential amplifier, has a very hard time, very hard life, because the input voltage has a difference that is, let's say, 200 millivolts, but these two voltages that are 200 millivolts apart swing up and down very fast over by a value that is big, could be 100 volts, could be 50 volts, or whatever it is. So this has a very hard time to work. This is the reason why I told you that section 4 is never used. Because in section 4 and 5 you can only use a resistor, a sensor resistor, and it's far better to have a constant voltage across it than having a swinging voltage across it. What about 2 and 3? Can you use a resistor in 2 and 3? Sure. In 2, a resistor is fine. In 3, a resistor is not such a good idea, because in 3 you have the very same problem as in 4. Besides other considerations, if you only have to want to measure your current with a resistor, and you can choose between 5 and 2, well, it's better to put your resistor.
Two is stressed as 4 because
2 is
stressed as the point 4 because when the switch is closed,
yeah,
we have the diode is off, so no.
we have to choose.
That
We have to place a resistor in 2 or 5. Which one will you pick? What considerations can you make about these two sections?
2.
2. Why?
Because the current is lower, so the power
Sure, that is a very good consideration, thank you. Power dissipation over here is, by this resistance, is smaller than over here. Because current through the resistor here flows only during D. Here it flows all the time. So if you do this cycle is, let's say, 30% or 70%, the power dissipation over here will be 30% or 70% of the power dissipation you have here. So from the power dissipation point of view, 2 is better. Any other consideration? Any other suggestion? That is very good. I like it. And in 2 you don't have too much noise due to the common mode swinging voltage. Between 2 and 3, there's another difference. What is the average voltage, the common mode voltage over here? What is the common mode voltage over here? Common mode voltage means the average voltage of these 2 nodes. About. Here, the common mode voltage is in, because both of them are about a V. And here, the common mode voltage is V naught. V naught is lower than V. And in many cases, the input voltage is the most positive voltage that you have. So if you come in at 12 volts and you have to go to at 12 volts level to measure a difference of 100 millivolts to 100 millivolts, can be done, but usually it's more complicated, more difficult to do than measuring it over here. Here you have an input voltage that is 12 volts, you supply your control system at 12 volts, and here you have, for example, 5 volts. So measuring 5 volts, the difference between 2 voltages is around 5 volts. If your supply voltage is higher, it's easier. Your common mode voltage range has not to reach the positive range. In many cases, with integrated ICs that have inside everything inside except the sensing resistor, the sensing resistor is placed over here. It's placed on the series inductor. You dissipate more power, that's okay, but inside the IC you can measure it easily. If your IC is supplied by this input voltage and you want to measure a voltage, a small difference, the same voltage as the input could be difficult. Can be done, but it's not so straightforward. Here it's easier. What if you put your sensing resistor over here in 9 or 10? Well, you have the same problem of power dissipation. 9 you have more power dissipation, in 10 you have less power dissipation, and both of them have a common mode voltage across them that is 0. So you don't have any terms of common mode, but you're just screwing up the reference voltage of your load that is not exactly the same as the reference voltage of the input. Okay, so that's good. So, for our sensing resistor, the 2 important numbers to be defined are Rs, the value of the resistance, and the value of the resistance is equal to, as any resistance is a voltage divided by current. The voltage across it divided by the current flowing through it. So the current is at peak. You have to pick the maximum peak of your current difference potential. Pick peak. Peak is a so-called lax vowel, and peak is a tense vowel. Tense or lax refers to the muscles of the mouth here around the lips. When you say peak, you have to pull on these muscles. When you say pick, you have to relax these muscles. And many vowels in the English are relaxed. There are very few that are the so-called cardinal vowels. The other are just relaxed, are just slipping by. Anyway, you pick the IIP maximum, absolute maximum, worst case, and what voltage do you want across your sensing resistor? it's the maximum voltage that your controller can accept at the input. And I told you, most of the time it's 1 volt, in some cases 0.25 volts or less, but 1 volt is the standard for many ICs. So, the current sense max typically is around 1 volt. Many ICs, when the input voltage coming from the current sense reaches 1.1 volt, no matter what, they shut it down everything, because it means something is going to get bad. So at least they protect the switch. Yesterday I was working on a color model order. I made a short circuit, and guess what? I got a big explosion from an MOS resistor because I was able to, with my short circuit, to cut the current sense